In our final videos, we're going to be looking at the free energies. We'll be taking a deeper look into these to see what they actually mean and what they mean in a chemical context. Now, we've already discussed what a free energy is. It is the fact that this is a maximum energy that's available for work. And remember, when we say free, we mean available, rather than free beer. The energies themselves arise from consideration of the second law of thermodynamics. So remember, when we think of our second law, we think of this delta S total has to be positive. Okay, we have to have an increase in the overall entropy. But thinking about the system and the surroundings is somewhat cumbersome. And remember that because the surroundings can be accounted for by the Clausius inequality, the change in entropy of the system gives us an indication of the free energy available. We've introduced both the Gibbs and the Helmholtz free energies. We've introduced both the Gibbs and the Helmholtz energy, and it's worth taking a little bit of a look into each of those and the circumstances under which they apply. The Helmholtz free energy, as we said, is the maximum energy available for work at constant volume. So we can convert readily between our internal energy and our Helmholtz free energy simply by adding or subtracting T delta S terms. So this works under constant volume processes, which is a very particular situation. In a laboratory setting, we would typically only consider our Helmholtz free energy at constant volume in a bomb calorimeter. The reason we look at it in the context of this course is that it works very well with statistical considerations of entropy. So everything we talked about in terms of lattices and everything, that is a constant volume setting. And it allowed us to explore the principles of entropy in those circumstances. So if we go back to those situations, so remember we considered a container as a lattice with a constant number of sites, which means they therefore have a constant volume. So if you have a container such as this one, we say the gas expands to fill the available space because those random distributions maximize the multiplicity within the container. So in this setting, where we have 6 gas molecules and 3 empty spaces, we have an overall multiplicity of 56. There are 56 different ways of arranging that particular system. If, however, we restrict the gas molecules to only exist in 6 lattice sites, we get to a point where we only have 1 empty space, and there's only 6 possible permutations for that. Therefore, it's advantageous for the gas to occupy as much space as possible within that because it gives more permutations. Under these settings, the constant volume model works well, so that allows us to consider entropy statistically and in a fairly straightforward way. However, in a lab, we very rarely work in constant volume systems. So what happens when we allow the volume to change? Well, let's consider an example system here. Let's allow volumes to vary. So we're going to look at gas expansion, but we're still considering an overall fixed volume. So we're going to put a boundary between 2 chambers. So we have an upper chamber, a top chamber, and a bottom chamber. Now the volume of each of these can change, but the overall volume of the two is the same. So we're kind of getting towards a varied volume example, but still in the safety zone of having an overall fixed volume, because that allows us to easily calculate the entropy. So the rules we're going to set here is that the gas can't diffuse through the boundary, and all we're going to do is we're going to allow the boundary to move itself. And at each time, we're going to determine the multiplicity. So in this setting, let's calculate the multiplicity of the top chamber. So we have 4 gas molecules in 4 lattice sites. So there's only one way of arranging this. There are no spaces possible. So our multiplicity is 1. When we look at the bottom, we have 2 gas molecules, but 6 other spaces as well for a total of 8, which gives us 28 different ways of arranging this system. Now we want to calculate the total entropy. Remember, the total entropy is a sum, which means when we look at the logarithmic relationship, we simply multiply the numbers together. This gives us a log 28 term, a relatively low number. Now remember, your rules of logs mean that if we want to find the total entropy, we add the entropy of the top and the entropy of the bottom together, which, because of your rules of logs, when we take them together, we're simply multiplying together inside the log. Make sure that you're happy with how to manipulate logarithms because we'll reuse them a lot on this course. Okay. Let's allow the boundary to move down. The gas on top expands, pushing the gas on the bottom down. So that barrier moves down and the volumes are now equal between the 2 settings. So we have 6 lattice sites above and 6 lattice sites below. So let's calculate the multiplicity of the top. Well, we have 6 sites total. We have 4 gas molecules and 2 spaces, so our multiplicity is 15. At the bottom, we have a very similar situation where we have 6 lattice sites. 2 of them are occupied, 4 are unoccupied, so we actually end up with the same multiplicity. When we calculate our overall entropy, we end up with a log 225. That's a substantial increase on what we had before. But can we still increase the entropy further? Remember, the volumes are now equal. So what happens if we allow that barrier to move down again? Okay, so now we get to a point where we have the volume on the top is larger than the volume on the bottom. We've allowed the pressures to equalize. So the pressure we have here is 2 lattice sites for each gas molecule on the top and 2 lattice sites for each gas molecule on the bottom. So the pressures are now equal. Well, let's now calculate our multiplicity. On the top, our multiplicity is increased to 70, but on the bottom, our multiplicity is decreased to 6. So when we calculate the overall multiplicity, we find that we have a log 420. So this is a considerably higher entropy than we had before. Remember, we were going from 225 to 420, meaning that we have an overall increase in entropy. So the increase in entropy on the top has compensated for the decrease in entropy on the bottom. Now, can we increase that entropy any further? So let's allow the barrier to move down one last time. Now we have unequal volume and pressure between the two. So we calculate the entropy at the top. Again, the entropy is increased to 210. But now at the bottom, there's only one way of organizing the system. So we see a net decrease in the entropy. We have a log of 210 overall. So that net decrease shows that we've passed the maximum value for our entropy for that system. And this results in the barrier being pushed back up to the previous setting. Now this is a model where we have a variable volume in the top and the bottom, but as we say, we've got a fixed volume overall. So let's turn our attention now to the Gibbs free energy. We say this is the maximum energy available for work at constant pressure, and we had the definition that we're familiar with, the Gibbs equation, but the rules of statistical entropy still apply to every setting that we work at. However, because we now have constant pressure, we're allowing our volume to change, it becomes more complex to calculate statistical entropy. This is why we address the rules of statistical entropy in the context of Helmholtz energy, even though Gibbs is where we predominantly work. So going back to the Gibbs energy. Remember we said it's an indication of the total entropy change of a system. So we have our delta H is equal to minus T delta S for the surroundings. Okay, so that accounts for the entropy change of the surroundings via the Clausius inequality, and the T delta S of the system. So the Gibbs energy change of the system reflects the overall entropy change in the entire system and the surroundings together. So remember, by the laws of thermodynamics, the second law, we have to have a positive entropy change which forces a negative delta G. So we're accustomed to the idea of delta G being negative for a spontaneous process. But remember, that Gibbs relation puts everything in terms of the system. We don't need to calculate the entropy of change of the surroundings because it's all accounted for in terms of the Gibbs energy of the system. And fundamentally, the negative delta G for a spontaneous process is a result of maximizing the total entropy. When we consider what's going on in a reaction, we want to balance the entropy change and the enthalpy change. So the Gibbs energy is fundamentally a balance. Remember, for a spontaneous process, delta G has to be less than 0. So if we write it in the equation like this, and then rearrange to just consider the entropy and enthalpy, all we've done is we've added T delta S to both sides of this inequality. So the enthalpy change has to be less than the product of the temperature and the entropy change. So in order for a spontaneous process to take place, delta S has to be greater than delta H. And temperature can fundamentally become the deciding factor in this. So if we think of it as a balance, we simply have a seesaw, and we want to make sure that the right-hand side is the bigger side. So we can drive a reaction forward or backward simply by changing the temperature. If we increase the temperature, we increase the weighting on the right-hand side, which drives our reaction forward. And at high temperature, this T delta S can become dominant, while at low temperatures, it isn't dominant. This is one of the reasons why we heat our reactions, to drive things forward. It also increases the rate of reaction. It's worth us now giving some attention to the standard state and what the standard state means. This is something you've seen a lot, but it's worth just quickly highlighting it. Most of the values that we cite are standard values, so the standard Gibbs energy, the standard enthalpy, and the standard entropy of a particular process. The definitions are fairly clear-cut, so we have things happening at the standard pressure, or standard concentration, standard pressure, and behaving as an infinitely dilute solution. These are definitions which are available in the IUPAC book, Quantities, Units, Symbols in Physical Chemistry, collectively known as the Green Book. But notice in all of this, there's no mention of temperature. There's no requirement for a standard temperature for standard conditions. Standard conditions merely express concentrations and behavior. So depending on the temperature of our solutions, the temperature of our reactions, the values for delta G will change. So you'll often see delta G written like this with a temperature specified. This particular would be the standard Gibbs energy at 298 Kelvin. When we think of the behavior of the Gibbs energy, remember that we do very few reactions at standard conditions. Our temperatures are frequently considerably greater than 298 Kelvin, while our concentrations are usually smaller than the standard concentration. So what we want to think about is something called activity. And we use this activity to describe behavior. The activity can be thought of as the relative fraction of the pressure or the concentration relative to the ideal concentration or our standard concentration. One of the important definitions to recognize is that for pure gases and solids, the activity is equal to 1, so we only worry about liquids when we consider about this. By looking at activities, this allows us to actually find the Gibbs energy of a particular process relative to the standard Gibbs energy expressed. And it's important to be able to make this adjustment because, as I say, so many of the things that we do are away from standard conditions. So if you want to make accurate predictions, we need to be able to do these adjustments. All of this will be covered in more depth in year 2. We often want to rescale our Gibbs energy. So we have this equation which allows us to rescale it. But what we see is once we start substituting the activity terms in, so if we're looking at the Gibbs energy at a particular concentration or the Gibbs energy at a particular pressure, we see the same RT log relationship cropping up time and time again. Fundamentally, this demonstrates the effect of temperature on the Gibbs energy. So everything we do is affected by that temperature. So let's look at how the temperature affects the Gibbs energy. We spoke briefly last semester about how it affects the phase transitions. So if we look at the molar Gibbs energy, again, familiar equation, but the molar Gibbs energy is affected by our temperature. We're used to seeing the change in here, but we're just looking at the absolute values. But remember that everything can change. As I say, everything with that temperature can change. If we look at the structure of this equation, we see we can plot how the molar Gibbs energy changes with temperature. And straightforward analysis of this equation shows that it is an mx plus c type equation. We should expect a straight line. If we're plotting G against T, we'd expect a straight line with a gradient of negative S. We are, of course, assuming that neither the entropy nor the enthalpy vary with temperature. So we're just considering the variation of the Gibbs. And we do indeed see a straight line when we examine this. To put this in mathematical notation, our gradient, the rate of change of the Gibbs energy with respect to temperature at constant pressure, is negative entropy. So what? Well, let's look at what happens with solids, liquids, and gases. Remember that the state with the lowest molar Gibbs energy prevails, this state of energy minimization, which results from that maximizing the entropy available. We're familiar with this setting in reactions, so we would expect to see the same behavior for a reaction where entropy remains a main driving force. If we plot the change in molar Gibbs energy for temperature, for a solid, we would see a particular straight line. When we do it for a liquid, remember, has a greater degree of randomness, it has a greater degree of entropy. There is more ways of organizing the liquid. So we'd expect to see a steeper gradient. And once again, when we look at the gas behavior, we see an even greater increase in the ways in which we can organize that system, a greater degree of randomness, so we see a much steeper gradient again. Remember we said that the state of molar Gibbs energy prevails, so we'd expect in this zone, we would expect to see a solid dominating. In this zone, we'd expect to see the liquid dominating, and in this zone, we'd expect to see the gas dominating. And these crossing points become important. This now starts to describe the process happening as a solid is heated and melts to form a liquid. It's heated again and then boils to become a gas. So this neatly explains the concept of colligative properties, and when you start thinking about solutions, you'll see what happens to the Gibbs energy and hence the boiling points and melting points as we dissolve materials into liquids to form solutions. So the Gibbs energy has a number of different meanings depending on how we're choosing to explain it. There are a number of different ways of understanding it, and we're most familiar with these energy profile diagrams. We've discussed about how it accounts for entropy change of surroundings in terms of the system. This is all really quite abstract. But what does it actually mean in a chemical sense? Because this allows us to get a bit more of a handle on it. In order to do this, we're going to need to turn to a little bit of mathematics. You might find it useful to write down equations and highlight what's happening, because this is actually really quite a fundamental recognition of what the Gibbs energy means. Let's go back to the first law. Now remember, we worked through, and from the second and first law combined, we derived the Gibbs equation. So let's go back to this equation. Let's consider it in differential form. This simply means that rather than considering a macroscopic change, which is what the big delta means, we're looking at a tiny infinitesimal change, this little d. And we're going to look at first at the enthalpy change. So remember the first law. The first law said that the change in the internal energy was the sum of the heat flow and the work done on the system. And under constant pressure, the definition is that our heat flow is equal to the enthalpy. So this allows us to do a quick substitution, still first law consideration under constant pressure. But what this does is it allows us to make delta H the subject and get an expression for our enthalpy. What we can now do is substitute this term back into our original Gibbs equation, and we can rewrite it as follows. Okay, so what we're going to do is we're going to look more in detail at the work concerned. There are many different types of work, but we're just going to focus on two broad categories. It can be divided into two terms, one of which is expansion work, so as a gas expands against a pressure, and we're going to look at non-expansion work, which is almost everything else. Let's go back to our internal energy. We can substitute it again. So we can write it as the heat flow, remember, and then the overall work done in the system, but we're now dividing this into our non-expansion work and our expansion work. And this allows us to substitute our internal energy one more time. Okay, things are getting a bit busy, but you can see that we've replaced our internal energy with this new term here. Now, if we consider what's happening under reversible conditions, our expansion work is simply equal to P dV. So what that means is these two terms cancel out, and we end up with this new expression for our Gibbs energy under reversible conditions. Okay, let's go back to the second law. What did we talk about in the second law? Well, if you remember the Clausius inequality, they simply said that for a reversible situation, the integral of the heat flow over the temperature is equal to the entropy. Okay, let's do a quick rearrangement. We can see that we're going to get an expression for T ds. This is telling us that our reversible heat flow is a product of the temperature and the entropy change. Okay, so this we can now substitute into our equation. But let's look again at this reversible heat flow. If we allow reversible heat flow to happen at all stages, well, the reversible heat flow is simply equal to the heat flow. So this dq and dq rev cancel out again. And under reversible conditions, we say that our Gibbs energy is simply equal to the non-expansion work. So what is this non-expansion work? Well, we often think of work in mechanical terms. So in physics classes, you'll have thought about it in terms of force times distance. In chemistry, we spoke about pressure times volume. You can think of a force being applied here. But both of these are mechanical, and particularly pressure times volume is an expansion work. But we want to consider chemical work. We can use that energy to do so much more than just expand pistons and cylinders. So if we think of electrochemistry, a battery working to drive a current around an external circuit and light a bulb, or do more interesting things. Or if we want to think of biochemistry, where we think of what's happening inside our bodies, happening inside our cells. So let's look at what goes on in electrochemistry. Electrochemical potentials, we're familiar with those, we're familiar how to handle them, but they indicate the thermodynamics of these cells. We can calculate the Gibbs energy very, very easily. And this is telling us about the electrochemical work being done in that cell. There's no expansion being done, but there's definitely a transfer of energy, which allows us to do that electrochemical work. It is non-expansion, but we can very easily calculate the Gibbs energy. And that tells us a bit about the chemistry going on inside that cell. If we think about what's happening in biochemistry, once again, the biochemical potentials drive thermodynamics of cells, and they're fundamentally based in equilibrium. Again, we'll do more of this in second year, but these equilibria are crucial to biological processes. If we think about the Gibbs energies of hydrolysis of ATP, at school you may have been introduced to ATP as the energy-carrying molecule, adenosine triphosphate. The hydrolysis of this releases a lot of energy. It drives cellular processes, this non-expansion work. It can drive protein folding and protein building. It can drive muscular contraction, which in turn provides mechanical work, and many other things. All the processes that go on inside our body rely on this hydrolysis, rely on that Gibbs energy doing non-mechanical work. Free energies are a complex subject, but fundamentally they are the maximum energy available for work, available for that non-expansion work. The Helmholtz energy, remember, is at constant volume, while the Gibbs energy is at constant pressure. And we can consider the Gibbs energy in two ways. They're complementary, they're not contradictory. It accounts for the entropic change of the surroundings, and it details the maximum non-expansion work we can do. And it's fundamentally an indication of the energy transferred in chemical processes. I hope this video series has given you more of an insight into the energetics of molecular processes and fundamentally what each of the laws of thermodynamics contribute in terms of free energies. Using this material, you'll be able to have a better understanding of the processes happening in all branches of chemistry. So please do ensure that you ask any questions of which you're unsure yourself.